have you ever just stopped and thought about the magic behind saying, "Hey Siri"? I mean, how a simple phrase, spoken into thin air, can wake up a device that's been totally silent. It feels effortless, right? But behind that simple command is an incredible secret journey. And today, we're going to follow the path of your voice, from a tiny wave in the air to a command a machine can actually understand.
Okay, so let's get right to the heart of it, because this is the central mystery. If your phone's microphone is always on, just waiting for you to say that phrase, why isn't your battery dead in a few hours? That's a huge engineering problem, and honestly, solving it required some absolutely brilliant thinking.
So to figure this out, we're going to follow the signal through 4 key stages. We'll see how your voice becomes an electrical signal, how it survives a gauntlet of digital noise, how it gets turned into pure digital data, and finally, how it meets the low-power guardian that's listening 24/7 without killing your battery. Let's start at the very beginning. Our journey kicks off right here, at the microphone. This is the first gateway, where the physical energy of your breath, of your voice, gets captured and turned into something the phone can actually start to work with. You see, modern phones use something called a MEMS microphone. The easiest way to think about it is like a microscopic eardrum, but it's made of silicon. When sound waves, literally the pressure from your voice, hit this tiny little diaphragm, it vibrates. And that vibration creates a raw, analog electrical signal that is a perfect mirror of your voice. Now you might think everything is digital these days, but Apple specifically chose an analog microphone here for 2 really smart reasons. First, zero latency. It's instantaneous. Sound goes in, electricity comes out, no delay. And second, you get much higher fidelity. It sends a pure, unprocessed signal, which, as you'll see, is absolutely crucial for what comes next.
This analogy from the source material just nails it. Instead of having a tiny, limited microphone process the signal right away, like a pre-cooked meal, you send the raw, high-quality analog ingredients to a much more powerful and specialized audio chip. That's the Master Chef. And that's how you get the best possible result, especially somewhere noisy, like at a concert.
Okay, so we've got our pure, high-quality analog signal, but its journey has really just begun. And this next part, well, it's incredibly dangerous. It has to travel through the internal battlefield of the phone itself. The inside of your phone is an absolute storm of electromagnetic interference. You've got Wi-Fi signals, Bluetooth, the cell antenna, high-frequency signals from the CPU. It's chaos. Our tiny, weak audio signal is like a whisper in a hurricane. It's at risk of being completely drowned out. So, how does it survive?
Well, engineers use this incredibly elegant solution called differential signaling. It sounds complicated, but the idea is just pure genius. You basically use the enemy's own power against itself.
Check this out. Instead of sending the signal down one wire, it's sent down 2. One wire carries the normal signal, and the other carries an exact copy, but flipped completely upside down. It's inverted. As they travel through the phone, any of that electrical noise hits both wires equally. Then, at the destination, a circuit subtracts the inverted signal from the original one. The noise, since it's identical on both, just cancels itself out and disappears. But here's the real magic. When you subtract the inverted audio signal from the original one, you actually double its strength. So the noise is gone, and the signal is now twice as loud. How cool is that? All right, our little signal has survived the battlefield. It's clean, it's strong, but it's still an analog wave. And the phone's processors, they don't speak that language. They speak the language of ones and zeros. So it's time for the great transformation.
This transformation happens inside a dedicated chip called the audio codec. This thing is our master chef and our master translator all rolled into one. Its main job is to take that smooth analog wave and convert it into a stream of digital data with unbelievable precision.
Now get this, the codec doesn't just take a few snapshots of the audio. It uses a technique called oversampling. To capture human hearing, you technically only need about 48,000 samples a second, but this codec, it takes over 6 million samples every single second. This total overkill is actually the first step in a brilliant process to achieve digital purity.
All that crazy oversampling lets engineers do a clever trick called noise shaping. You see, the process of going from analog to digital always creates a little bit of error, kind of like fine digital dust. We call it quantization noise, and this analogy is just perfect. Noise shaping is like a magic broom that sweeps all of that dust into a corner of the room where you can't see it or hear it.
So, before noise shaping, you can see that this digital dust is spread all across the frequency range, and that includes the part that we can actually hear. It just degrades the quality of the whole signal.
But after noise shaping, look at this. The audible frequency range is now pristine. It's clean. All of that noise has been pushed, or shaped, way up into the ultrasonic frequencies that are far beyond what a human can hear. The result? An incredibly clean digital audio stream.
We've got it. A perfect digital representation of the voice. It's clean, it's accurate, and it's ready for processing. We are now at the final leg of our journey, where we finally uncover the secret to all-day battery life.
But before we get to the final destination, there's one more really fascinating detail. You'd think the main CPU, the powerhouse of the whole phone, would be in charge of everything, right? Well, when it comes to audio, it's actually the other way around. The specialized audio codec acts as the master, and the mighty CPU is the slave.
So why do they do that? It's all about quality. The audio codec is an expert at creating a perfectly stable, clean clock signal, which is like the heartbeat for digital audio. The CPU is just too busy and noisy. By letting the codec dictate the timing, it prevents something called jitter, tiny imperfections in that heartbeat that would totally distort the sound. Quality always comes first.
So, this pristine, perfectly timed stream of digital audio is finally ready. It's heading for the processor, but it doesn't go to the main CPU, that power-hungry sleeping giant. No, it gets rerouted to a secret destination.
And here it is. This is the hero of our story, the always-on processor, or AOP. This is a tiny, incredibly efficient little coprocessor whose one and only job is to stay awake and listen. While the main CPU is fast asleep, saving massive amounts of power, the AOP is on duty, just sipping the tiniest amount of battery. And this is how it all comes together. The AOP is constantly monitoring that high-quality audio stream coming from the codec. It's running a tiny, specialized neural network that's been trained to do just one thing: recognize the unique sound pattern of Hey Siri. It ignores everything else. And only when it detects that perfect match does it send the wake-up call to the main CPU, bringing that sleeping giant to life to handle your request.
So there you have it. That's the solution to the paradox. It's not just one trick, but 4 pillars of brilliant engineering all working together in perfect harmony. You've got differential signaling for a clean signal in a noisy world, sigma-delta conversion for digital perfection, the codec as the master for flawless timing, and finally the always-on processor, the low-power guardian that lets your phone listen constantly without killing the battery.
This whole incredible symphony of engineering was designed to perfectly capture a real human voice. Which leaves us with a final, fascinating question for today. In an age of AI-generated audio, could this exact same high-fidelity system be used to spot a fake? Could it learn to detect the tiny, unnatural flaws in a deepfake voice, becoming a guardian not just for our commands but for authenticity itself? Something to think about.